Hello, everybody. So today we have another rank booster on steady state approximation. This is actually a beautifully crafted question. Now, if you go through the question, you can understand that they have given a question regarding the thermal decomposition of acetaldehyde, which follows a chain reaction mechanism. And they say that methane gas is produced in the propagation step. You have to find the rate of methane formation, and it is proportional to following options are given. So the problem is in this question, this is actually a very good question, but then the mechanism was not given. So only those students who knew the mechanism were able to solve this. Otherwise, we'll have to skip this question. Now, for you people, I have already added the mechanism. Okay. So this happens in 4 steps. I have added the mechanism. Now, I request you to pause the video, look at the steps which are given in the mechanism and try. Okay. Yes. So please go ahead. Once you have done, you please come back and watch the video solution. Okay, so let's start. So in the mechanism, you can see that it happens in 4 steps. And the question that they have asked is regarding the methane formation. So methane is CH4, correct? Now CH4 is formed only in the second step, as we can see over here. So if we have to write the formation of methane with respect to the time, which happens only in the second step. So we can write it as equal to K2 into concentration of CH3 into concentration of CH3CHO, which is acetaldehyde. So already in the question, they have given that it is a thermal decomposition of acetaldehyde. So acetaldehyde is our reactant and CH3 is our intermediate, which we are supposed to eliminate. So there is no equilibrium in any of these steps. So we have to approach the steady state approximation. So this is our first intermediate. So let's label this equation as equation number 1. Now in equation number 1, we have an intermediate. We have to remove that intermediate. So to remove that intermediate, we will apply steady state approximation on CH3. Correct. Now, if you apply steady state approximation on CH3, we'll be able to see that changes in the concentration of CH3 with time will be equal to 0 according to the steady state approximation. Correct? Now, let's come back to the mechanism. Let's come back to the mechanism and see how is the concentration of CH3 varying with time. So we can see that in the first step, CH3 is being formed. Correct. So if it is being formed, it will be plus K1. The reactant of the step is CH3CHO, acetaldehyde. In the next step, it is disappearing. CH3 is disappearing. So if you want, I can highlight. In the first step, it is forming. In the next step, it is disappearing. In the third step, it is forming. And in the fourth step, it is disappearing. So we need to be careful of the plus and minuses. If it appears in any of the process, you'll put plus in front of the rate constant. If it disappears in any of the steps, you will put minus in front of the rate constant. Correct. So in the first step, CH3 is being formed, so you'll put plus. In the second step, it is disappearing, so you'll put minus. K2, the reactants are CH3 and acetaldehyde again. Okay. In the third step, it is forming. So plus K3, CH3CO. And in the final step, you have to be careful of the coefficient. Okay. It is disappearing. Correct. So if I have to write the rate of the reaction, I'll write it over here. If I have to write the rate of the reaction, it is minus 1 by 2 dCH3 by dt, that is equal to K4 into CH3 to the power 2, the rate of the reaction of this particular step only, fourth step only. Correct? Out of which, what do we need? We need only dCH3 by dt. So if I rearrange, dCH3 by dt is equal to, this 2 will go to the other side, minus will go to the other side. So it will become minus 2K4 CH3 square. So you have to be careful whenever you have coefficients. Okay, so this will form minus 2 times K4 CH3 2 times. And this is going to be equal to 0 as we are applying steady state approximation. Now, if you look at this equation, if I label this as equation number 2, if you look at this equation, you can see that in this equation, you have CH3, which is the intermediate that we are trying to eliminate. There is acetaldehyde, which is one of the reactant, so that is okay. But then there is another intermediate as well, this one, CH3CO. That is another intermediate. So we have to eliminate that one also. So can you see in the mechanism, CH3CO is formed in the second step. It is disappearing in the third step, and that's all. So we need to apply steady state approximation on CH3CO as well, because we don't want any terms regarding the intermediate. We don't want any terms regarding the intermediate. So next, we will apply SSA on CH3CO such that changes in the concentration of CH3CO with time is equal to 0. There are only 2 steps, right? So in the second step, it is being formed. In the second step, it is being formed. So it will be plus K2 and the respective reactants. So let's write it down. CH3CO divided by dt is equal to plus K2 CH3 and CH3 CHO it was. And in the third step, it is disappearing, and that one itself is the reactant. So if it is disappearing, you will put minus K3 CH3 CO. Now I label this as equation number 3. Okay. Now we know this is also equal to 0 because we have applied steady state approximation. So this is also equal to 0. Now, a very important step. For the sake of simplicity, what I'm going to do over here is I'm going to add 2 and 3. If I add 2 and 3, see what is going to happen. If I add 2 and 3, the second term, which is minus K2CH3 CH3CO plus K2CH3 CH3CO, these will get cancelled. Okay? And the third term of the equation number 2, that is K3CH3CO and minus K3CH3CO, that will also get cancelled. So I'm adding them up. So on the RHS, we have 0. 0 plus 0 is equal to 0. Okay. So this adding the RHS will give us 0. And after cancelling out all these, what we have is just K1 CH3CHO plus, no, not plus, minus 2 times K4 CH3 squared is equal to 0 is what I have. Now it is very easy. The only intermediate that we have is CH3. We can rearrange this. K1 CH3 CHO is equal to 2 times K4 CH3 to the power 2. If I rearrange this, CH3 is going to be equal to K1 CH3 CHO divided by 2 times K4. This is going to be CH3 squared. Now, if I want the value of CH3, I'll take root on both sides. So this is going to be the whole to the power 1 by 2. So this is my expression of CH3. I'll take it as equation number 4. Equation number 4. Now, coming back to the question, we need to find the expression for the formation, rate of formation of methane. And I'll paste it over here so that you can see it in one screen. So this is equation number 1. This is equation number 1, where you have the rate of formation of methane as equal to K2, concentration of CH3, which is an intermediate, into CH3CO. Now you have the expression of intermediate In terms of the reactant only, let's plug in. Okay, so we'll put equation number 4 in equation number 1. So we get formation of CH4 with time is going to be equal to, we are going to plug in this, okay? So we have K2CH3CHO, which is already there in equation 1. Now the expression of CH3 is K1 to the power 1 by 2, CH3CHO to the power 1 by 2 divided by 2K4 to the power 1 by 2. This is the expression. What is the question? They have asked that the rate of formation of methane is proportional to what? Okay. So in terms of acetaldehyde is what they have asked, correct? Now, in terms of acetaldehyde, the power of acetaldehyde over here is 1. The power of acetaldehyde over here is 1 by 2. So we can say that the rate of formation of methane is proportional to concentration of acetaldehyde to the power 1 plus 1 by 2 is 3 by 2. Option A it is. Option A. It is. Okay. A beautiful question wherein the simple step of adding equation number 2 and 3 is going to simplify your question very, 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 very much. Okay. But the problem is you need to know the mechanism. Otherwise, you won't be able to do. Okay. So that's all for this session. See you in the next.